So we've taken a little bit of time and reviewed what it looks like to simplify a square root, right? To solve a square root that is a perfect square. And what we're going to look at next is dealing with not only perfect squares, but imaginary and complex numbers. And so what you see here on the screen is something you will want to make sure that you have written down in your notes. If you are using the student note sheet, you will see that this is there for you already. This is simply a table that is reminding us of those perfect squares. Now remember, a perfect square means that it is a square of a number. So, for example, 1 squared is equal to 1, 2 squared is equal to 4, 3 squared is 9, and so on and so forth. But it'll be really helpful to have these written down so that you can look at them often. Okay, so what we're going to do is we're going to practice simplifying some of these roots. Now, this is kind of a review from when you dealt with trigonometry, which would have been in geometry. We need to review how to simplify these radicals. Now, if you need some more practice, I've also linked in Canvas an additional resource of walking through how to simplify these radicals, but we'll look at a couple of them. And I'll tell you, there's really a couple of different ways that you can think about how to simplify these radicals. The first one, and one that you may have been taught, was to look at our square root, look at that number that's in the square root, and think about what perfect square can I divide this by. So I know that this number, 24, I could break it into 4 times 6. Now, the reason I did that is because I know that 4 is a perfect square, and the square root of 4 is 2, and so we'll end up with 2 times the square root of 6. Now, if you want a different way to do it, maybe this one didn't make sense to you before, it's confusing to you, there's another way we can think about it. And what I would want you to do for this next one is to break this number down into what's called a factor tree. And so we want to break this number down into all of its factors, all of its prime factors. So 24, I may say, well, I know that that's 2 times 12. Those are 2 of the factors. We can start our tree. You may have broken this down into something else, and that's okay, as long as you take your tree all the way to its primes. And so what I'm going to do next is I know that this 2 is a prime number. So I circle it to remember it's there, but there's nothing else that we can do with it. And then I take my 12. I know that 12 is 2 times 6. Again, I circle this 2 because that's as far as I can go. And 6 is 2 times 3. Now these are both prime numbers, so I've hit kind of the end of my tree, and I see all my primes. And what this is telling us is that instead of the square root of 24, I could do the square root of 2 times 2 times 2 times 3. And what I'm going to look for is any place that I have 2 of the same number. You see I have 2 of those 2's. This 2 doesn't have a partner. This 3 doesn't have a partner. So any place that I had them partnered up, those numbers will come to the outside as a single number. These ones that didn't have partners need to stay in there. And so our final step is going to be to put that 2 times 3 back together. Now you'll notice that both methods, we get the same answer, just 2 different ways to kind of think about it. Okay, let me show you those 2 again. So here, square root of 40. If I think about my perfect square numbers, I could rewrite this as 4 times 10. And because 4 is a perfect square, you know that will become 2 times the square root of 10. Now, similarly to how I did before, I also could look at the factor tree and say, well, I know it's 2 and 20. That 2 is a prime, so I can't go any further. 20 is 4 times 5. 5 is a prime. Keep going with my 4. And here we've hit all of our prime numbers. And so what that means is that I could rewrite that square root as 2 times 2 times 2 times 5, and I look for any of those pairs, anything that has a pair will come to the outside. There will be a couple left inside, and then when I put those back together, I'll get 2 times the square root of 10. So this is how we simplify those radicals. Now, what we're going to kind of build onto that today is how to deal with these if they're not perfect numbers. So for example, in this first problem here, x squared is 16. So we know that x could either be 4 or a -4. And it gives us two answers, right? The positive or the negative. What if we have this problem? X squared is equal to -9. What numbers, when I square it, is going to get me a negative? Nothing. If we're just looking at 9, right, we could get -3 or 3, but this is a -9. And so we have to be really careful about these. What this is starting to have us look at is equations that no longer are real numbers, but they're part of a number system called the complex numbers. So the number square root of -1 is actually called the imaginary unit. This I is how we say the imaginary unit. There's an I under here, right? We just write it just like an I. So if I replace that square root of -1 with an I, then we're able to write the solution. So you'll see down here, x squared is -9 is either 3i or -3i. It's like we've taken that negative off the front of that 9 and made it into an I. And so that's what we're going to be taking a look at today. So these complex numbers have that I behind it. Okay, there's an imaginary number. Maybe you have an imaginary number that's 2i or 5i, right? Those are imaginary numbers. It's a number with that I. And complex numbers are written with both a number and that imaginary unit. So for example, you see a few here. Here's a complex number, right? It has a real part and an imaginary part. Here's another complex number. It has a real part and an imaginary part. This is even a complex number. It has a real part, right? It's just 0, and an imaginary part. Now notice that it is always written as a plus bi. We always are going to write it in this form. The real number plus the imaginary number.